Hey everyone, and welcome to Dr. Abu RTN Academy channel. Today we are going to discuss part 3 of the descriptive statistics and the biostatistics subjects. In the previous video, we have already learned how to represent the categorical data, okay, and the different way of charting them, whether it's pie chart or it is bar chart. And in this video, we are going to learn how to represent the quantitative data. Quantitative data, or representing them, or graphing them, or charting them. So in this video, we're going to know how to chart or represent or graph the quantitative data. So in the previous video, for the categorical data, we have learned that we could present them in the form of pie chart or bar chart, because the data are distinct. We have a limited number, even if we have a huge number or large number of the data, so we can get the top 10, top 5, top 3 and shortlist them. Okay, so have a smaller list so we can present them. Pie chart, as we said, it is a percentage wise of the 360 degree. Okay, as you can see here. The bar chart, we have for each category, we have one bar for each category, and these bars, they have some space. As you can notice here, we have some spaces, gaps between the bars, because they're not continuous. Okay, for example, X, which is blood group A, blood group B, blood group C, or green, red and yellow, Africa, Europe and America, whatever. So we have bar chart for everyone, and there is no relation between this bar and the next bar. Okay, and there are some gaps between them. For quantitative data, we have different ways to present them, because all of them are numbers, they're not categories, and we are counting how many numbers under each category. For each category, how many numbers? No. In the quantitative, we have number against each individual. This is the difference between, in order to avoid any mix between the categorical, and because a categorical also has counting, but we are counting how many number of individuals under each category. But in quantitative, for each individual, each person or each object, we have a reading, we have a measurement. Okay, so this is the main difference between them. So we have value for each individual. So here we can have the line graph. Sometimes they call it time plots. Because we usually in this line graph we have to access x-axis and y-axis. Okay, x-axis, something which is independently changed. So for example, we have the measurement after 1 hour, after 2 hours, after 3 hours, after 4 hours, and we get the measurement, the readings. Okay, so we'll have like line graph, could be straight line, could be curve, but at the end of the day it is continuous line graph. Okay, so few things we have to understand and fully digest before starting this quantitative data representation or charting or graphing, which will make our life easy in the next slides. Okay, as you can see here in this slide or this photo, which I'm just inserting, that we have the time series, okay, or the time graph or the line graph. This is line graph. Sometimes they are calling time graph, as we said, because x-axis here, it is time, based on the time. So 1 second, 2 seconds, 3 seconds, 1 hour, 2 hours, 1 minute, 2 minutes, 3 minutes, and so on. So if x-axis is factor of the time, so it's called time series, which in most of the cases which we have, most of the experiment we are taking with the time. Okay, it's changing with the time. So here, if we can see, I have taken reading at 1 minute, I have taken another reading at 2 minutes, I have another meeting at 3 minutes, reading at 4 minutes, another one at 5 minutes. So at each point, x-axis and y-axis, I have 1 point, x-axis, y-axis, I have another point, and so on. So the connection or the linking or connection of these points together by straight lines, this gives us the line graph. Okay, to connect this point by this point by a line, this point or next point by a line. Okay, so this is called line graph. If it is factor of time, so here x-axis is the time, so we call it time series or time graph. Okay, the benefit of this one, that initially we don't have, we have taken the readings only for few points. For this point, which as 1 minute, at 1 minute, the second point at 2 minutes, 3 minutes, 4 minutes, 5 minutes, and so on. So this at 1 minute, this at 2 minutes, okay? But what about 1.5 minutes? I cannot get the data because I did not do any experiment except for 1 minute and 2 minutes and 3 minutes, 4 minutes, 5 minutes. What about in between after 1.1 minutes, 1.2, 1.5, 1.7? By drawing this line, I can predict what is the results, what is the outcome of the experiment. So I can come here at 1 point, for example 1.3, and I can draw a line and I can get the readings for me. So this is the benefit of connecting these lines. That's why we have to make sure that when we connect these lines, we are connecting them in the right way. Okay, I'll give you an example. So if we connected this line like this, and you want to take a reading in between, so what the reading will give? The reading will give you this reading. Okay, but if you connect straight line, you will get this answer. So this will be the reading here. If you connect it in this such way, this will be the answer. Okay, if you connect it the other way, like for example like this, so this will be your answer. So the three answers are different. So we have to make sure that we are connecting them rightly. Connecting them rightly, we have the best fit line, we have straight line connecting the points, and we have different methodologies. Okay, let us clear this one. Okay, so we'll come to the time series is a line graph because it is represented as lines. Okay, line graphs. Okay, uses straight lines to connect points. I have one point, another point, which I have got the reading from the experiment or from the measurement, so I'm connecting them. Connecting points plotted at the value of each measurement above the time. Okay, so I have here the time. I'm taking the measurement, for example, this measurement, and then I'm plotting it here. Okay, above the time it was taken. Okay, so just at 1 minute I'm plotting this one, at 2 minutes I'm plotting the 3 minutes, and so on. So I just on x-axis highlight the time or identify the time, exact time when I take the reading, and then go above it and or below it and plot it on the graph. Okay, for the histogram, many people, this is actually a big problem for many people. They are confusing between the histogram and bar chart or bar graph, because bar graph, which we have taken in the previous slides, if you can recall, we have drawn it like this. Let's use different color. Okay, so we have drawn it like this, same color. Sorry. Okay, so here in the bar chart, this is the first bar chart, this is the second bar chart, and this, let's assume this is the third bar chart. In the bar graph or bar chart, we have gaps between the column, between the bars. So I have this bar and I have this bar, and they have gaps between them. Okay, in the histogram I don't have gaps. All the data are attached to each other. Okay, they are jointing, there is no gap. Sometimes we find gap really in the histograms, but this gap, it's not because there is a gap in the reading. No, because the reading is 0. So if, for example, we assume this one is the frequency, if the frequency is 0, so the height of this column will be 0, so it will disappear. You will feel it is a gap, but it's not a gap. There is a reading, but the reading is 0. But in the bar chart or bar graph, there is a gap, real gap. There is no reading has been taken here. It is categories. Okay, so data is discontinuous. I have here blood group A, blood group B, blood group C, and so on. So there is no data in between. Between A and B, there is no data. Between B and O, there is no data. Between O and AB, there is no data. Okay, so here in the bar chart there are, because bar chart is for categorical data. We have taken it in the category by chart and bar chart or bar graphs. We have taken them in the categorical data. Okay, where we have distinct data, so they are not continuous data. So always there are some gaps here in the bar chart. So this is the bar chart or bar graph. Okay, or graph. But in the histogram, data must be continuous. Okay, if you find any gap here in between, one of the column is deleted, it is not a gap, the value is 0. Okay, for example, the frequency, the value of the frequency is 0. In this histogram is a bar graph, so it how we represent it by bars. So I have 1 bar, 2 bars, 3 bars, but it is not must that all the bars are equals in the width. So this here I have the widths are the same. So on x-axis the deviation are the same. Okay, this called deviations or bends or whatever. So these deviations are the same. I have start 0, 5, 10, 15, 20, 25. So every interval equals 5 in this example. It could be every interval 10, 0, 10, 20, 30, 40, and so on. 0, 50, 100, 150, 200. So every interval is 50. So it depends, but they should be equal. But intervals are equal, but it doesn't mean that I cannot have one bar here which covering two intervals. It could happen. Okay, so it doesn't mean that the width of each bar should be equal. Here the width of in the bar graph, the example which is just given now, the widths are equal. Okay, it could be a line, but because it's called bar graph, we are making it a line. Okay, but the width here meaning nothing, no meaning here. Blood group A, the width doesn't mean anything. Blood group B, blood group O, blood group AP. So the width doesn't mean anything, but here in the histogram the width has a meaning. So if it is this width, it has a meaning, so it's covering all this area. Okay, but here the width doesn't mean anything. We'll come now into the details or the differences between the bar graph and the histogram in the next example, which I'll give to you right now. So just let us read here. The histogram is a bar graph of a frequency distribution. Okay, so it shows us how the frequency is distributed. For example, I have 100 students, so I just put them, depends on their score. Some of them score between 40 to 50, or 50 to 60, 60 to 70, 70 to 80, and so on. So if I can see here, I can say that in this area, these are the most number of the people. For example, this is from 70 to 80. Okay, this is the bandwidth. So I can say from the first visualization or the first notice that I have most of the students has scored between 70 and 80. Okay, the second most is between, for example, 40 and 50. So this is actually the way how we are going to utilize and get the benefit of the histograms. So the histogram is a bar graph of frequency distribution of quantitative data. Okay, so here histogram, like line gram, we are dealing with quantitative data. The horizontal axis is the numbers. Okay, the grades which you are scoring, the number of plants, the number of years, the age, whatever, and here the frequency. Usually here the frequency. In some cases it could be different. Here could be, you have taken already in the high school, could be frequency distribution, and this is a different scenario which we'll come in touch when we discuss the histogram in detail. We'll come in touch with the frequency distribution. If y-axis is not frequency and it is frequency distribution, so how we can deal with such cases. Okay, frequency distribution, if you recall, equals the frequency. Okay, if this is the frequency divided the width. Okay, if I have two columns of, for example, this column is bigger in the width, so it will be the frequency divided this width. Okay, the width. Okay, so frequency divided the bandwidth. This is band 1, band 1, band 2, band 3, band 4, band 5, and so on. So the frequency divided the bandwidth. Okay, we have another way of representing this quantitative data, which called the stem and leaf plot. Stem and leaf plot, just to make it simple. For example, I have 34, I have 35, I have 37, I have 34 again, I have 59, I have 50 or 61, I have 63. So I want to represent them in a way it will be easy for me to recognize them. So what I'll do, I'll check the last. Here I have units and tens. So I take always the last or the biggest units which you have. The biggest one here, I have the units and 10. So the biggest units is the tens. So I put the tens as the stem of the tree. If you have the tree, this is the stem. So this is the stem of the tree. And this is the branch, okay? And this branch has the leaves of the tree, okay? So the stem is the main chunk, okay? So here, if I want to write this number, I write this. The tens start with 3. So what is else with 3? I have 3 and 4. I have to put them in order. This is the one of the most important. So I have 34, I put 4. Another 4, I put 4. Another 5, I put 5. Okay, 5. I have 7, I put the 7. Even if they are not in the order, I have to arrange them. So when I put them here, I have to put them in order. So I have to put key here and write key 3, 4 equals 34. Okay, we'll come into this stem and leaf in details, and it's very simple and easy way. If it is decimals, if it is hundreds, if it is tens. So here just tens, 34, 35, 37. So coming to the 60, for example, if I don't take 61 and 63, so coming to the 60, I have to write here 40. I don't have 4, so 5. I have to write 5. I have only 5 and 9, 59. 59, 60, I have to write 6, 1 and 3, so 61, 63 and so on. This will come to it into detail. So a stem and leaf plot retains the original data, it leaves the original data. The leaves, okay, are the last significant digit. So here the last significant is 4, so I put it here. Here's 5, I put the 5 here. 7, I put the 7 here. But the stem or the main bulk, I have to put it in the stem. Okay, we'll come to this one into details when we discuss the stem and leaf plot. Okay, the last significant digits I put as leaf. Okay, significant digits in each data value, and the stem are the remaining digits. So take only the last significant, which is on the right. I put them, all of them, as leaves, and only the last digit on the left, the biggest one, I put it as stem. So coming back to the main slide, which we have the line graph. Okay, it's called also time plots because we are plotting it time against the frequency or the value which you are measuring here. Okay, the variables, which is height, weight, whatever. Okay, the variable. Okay, so when you use when there is a meaningful sequence. So I have here sequence to the time here the value increased, here another value, here another value, here third value. Meaningful sequence like time. Okay, this is the sequence of the event, how it is progressed along with the time, or class wise, class number 1, class number 2, class number 3, and in each class I have the marks of the students, or I have the time. After 1 minute, this is the reading of the experiment. After 2 minutes, the reading of the experiment, and so on. So it should have meaningful sequence on the x-axis. Okay, the line connecting the points. Okay, which help us to emphasize any change over the time, so we can see whether it's increasing or decreasing, or remains the same, constant. Okay, then the histogram and the stem plot. You remember the stem and leaf. Stem and leaves, which we have taken here, but 3 and 5, 3 and 7, 3 and 9, 5, 7, for example, 1, 2, 3, 4, and so on. So here it's called 35, 36, 39, and so on, 51, 52, 73, 74, and so on. It's called the stem and leaf. And the histogram, we have taken it, which is like the pie chart, but they're continuous. Okay, it could be like this. Okay, this is called histogram. There are summary of the graphs for a single variables. Okay, these are summary of the graph for single measuring the height, the frequency of the height, of the length, of the weight, of whatever. Okay, They are very useful to understand the pattern of the variability of the data. So from here I can see, okay, most of the data are here because this is the biggest area. Okay, this is the second biggest area, although it is higher, okay, the number of frequency, but here the area is bigger. Okay, so I can, from here I can identify or recognize the variability, how the data is varying, how data is changing. Also we have other graphs to reflect numerical summaries. Okay, in this slide we are going to discuss the line graph, the first one of them, which is line graph, or we call it time plots. In time plot, time always goes in the horizontal x-axis. So here always the time could be years, year 1998, 1999, 1990, 1991, and so on. Could be hours, could be minutes. So it must be one of the time parameters: minutes, second, hours, years, decades, whatever. Okay, so it's always goes, time always goes as horizontal or x-axis if we are talking about the time plot. Okay, when we describe a graph talks about the time, so we have to do two things. We have to describe the time series as far as we go with the time, the number of years, what happening. Okay, is it the trend is increasing trend or decreasing trend? So we look in general about the pattern, the overall pattern of the data. The data is going up and down, up and down, up and down, but the trend of the data here, the trend is like going up. Okay, so this is called the trend. When we describe the time series, okay, this time series, we are looking at the overall pattern, not every and each one, the overall pattern. In the overall pattern we'll see the trend is going down or going up. Okay, the overall pattern, and also for striking the deviations with the, okay, the trend is going up but the deviation is very close to the line. This one, okay, this is a deviation small, or we have a big deviations. So which one? So here we are looking at the overall pattern and the striking deviation and the deviation from the pattern. How big the deviation? So here deviation is very small, but here one of them deviation is big. Here deviation is big, because it is very far from the line. Okay, but in the main trend, it is very close to the line. So for those who forget what is the trend is the rise or fall. Is it rising or falling? The rise or fall that persists over the time. So here it is rising over the time. Time is passing and it is rising. So here y was here, and the second point after some time it's become higher. Y here become higher. So here the first y, second y, third y, and so on. Okay, so it is rising, a rise or fall. But if we have a declined line like this line, so here the y was the biggest, the second by the time, after the time passed, this is the new y, the third y, and so on. So the y was biggest one, second y here, third y is here. Okay, so the y is declining down. So the trend is a rise or fall that persists over the time despite the small irregularities. Okay, so here we should not pay a lot of attention to the small irregularities. Here we have one irregularity, here we have another irregularities, here another, but the trend itself, it is going up, rising trend. Okay, and the deviations is it is almost very close, except in some area, some irregularities here and there. Okay, this irregularities we have also, it's called the pattern that repeats itself. You remember in climate we have seasons. We have the summer, we have the spring, then summer, then autumn, then winter, and they keep repeating. Okay, spring, summer, autumn, winter, spring, summer, autumn, winter, and so on. So here also they're repeating. Okay, if they're repeating in the same sequence, that's called seasonal variation, which is repeating itself like the year seasons. Okay, so it's repeating itself. Okay, but it might be in some cases with high fluctuation, like this one. See, high fluctuation, and it could be also very close to the main line. So a pattern that repeats itself at regular interval every 2 years, between 1988 to 1990 to 1992, 1994, 1996, so every 2 years. Okay, so we look how they are repeating themselves every 2 years, how they are repeating themselves, okay, over the time. So it's called seasonal variation. As we can see in this slide, we can use also this time plot to compare the data. I have in this table, for example, this influenza epidemic, okay. For this influenza epidemic, we have week 1, week 2, week 3, week 4, and so on up to week 17. And they have the number of cases who got this influenza. 36 in week 1, 532 in the week 2, 4,233 in the week 3, and so on. The death, okay? So this is the case which infected by influenza, but doesn't mean that if someone got infected by influenza, he will die. So here the number of cases 36, but this is 0. 531, but this is 0, and so on, okay? So if we plot this two, so week-wise, week is the time, okay? Like week, like year, like dates, minutes, hours, second, and so on. This is the time. So it will be on the x-axis, okay? So I put here week 1, week 2, week 3 on the x-axis, okay? Okay, and again in this one, I plot for week 1. I have one line graph for the cases which infected, and another line graph for the death, and I'll see is there any relation or no. So the first thing I have to look at is the axis, x-axis. It will be common for both of them, for the cases and for the death, week 1 up to week 17. So I put for them from week 1 up to week 17, okay? It is not mandatory that I put everyone week 1, week 2, week 3. I can put week 1, week 5, week 10, 15, or I have to cover at least half of the page or 60% of the page width of the graph, okay? So it's better to have more data, but I cannot present 17. It's also too much. So I can have week 1, then week 3, then week 5, so I can skip 2 and put the third one, skip 2 and put the third one, and so on. So week 1, week 3, week 5, week 7, week 9, and 11, and so on. Okay, so I have a more visible number of week, okay, can be read, can be represented, and at the same time I can do something in between, okay. But when I put the axis itself should be readable. I should be able to read the data here. If I put 17, maybe the font has to be very small, so I cannot read it, okay. So the x-axis for both of them will be common, will be the same. X-axis will be from week 1 to week 17. What about y-axis? Y-axis, I have to check the smallest value and the biggest value to get the range. How can I split it? From where I have to start and how can I split it? I find that the smallest one is 36 and the biggest one is 8,000. So I cannot put 1, 1, 1 to 1 to 36, 37, 38. I cannot put tens. So I have to think about, because here we reached thousands. Maybe I have 10 lines only, or 10 squares I can use, 10, 12 squares. It should not be more than this, 10, 12, 15 maximum, because otherwise it will be a very big graph, okay. So if I find up to 8,000, I can use 1,000, because even if I use 500, it will be around 60. It will be a very long list, okay. So I can use thousands, 1,000, 2,000, 3,000, and so on, okay. But in this case, make sure that this 36, it will not appear, it will look like 0, okay. So here I have 8,600, so I have to put 0, 1,000, 2,000, 3,000. So this is my scale. But if I present all this data, all of them will appear in the first 1,000, because the biggest figure which I have here is 738. So if I use this axis to present one, so all the graph will come in this area. Let me clean this one so you can see it. So if I plot all this data, all of them starting from 0 up to the biggest one, which is 738, all of them will be in this area, okay. So the graph itself will be in this area, very small. I cannot recognize anything here, okay. It will be very small. I cannot reach even 1,000 by then. So in order to make it more visible, we can use two y-axes, or two scales for y-axis in different way. So how we can use to scale? On the left side we can use one of the scales which from 0 to 1000 to represent the cases, because cases from 36 up to 8000 something, which is 9000 or 10,000. So okay, so I can use this scale for the cases diagnosed, okay, and I can use the right y-axis to represent the death. Okay, so if I want to measure the, or if I want to graph or represent the death, I have to use or to measure through this y-axis. If I want to represent the cases, I have to use this y-axis. Okay, I hope it's clear. So by having this way, they have plotted the two graphs, and because the biggest figure here is 800, so I can see that I have used from 0 up to 800, and here from 0 up to 1000. Even if I look at the scale of this one up to 800 and this one up to 10,000, so if I said 800 divided 10,000, approximately we can say that this scale is 2 zeros with 2 zeros, 8 divided 100, so 8 divided 100 equals 0.8 or 8%. So I can say that this scale is 8% of this scale. Approximately, it could be more or less, because also we did not reach 1000 here. But here we have reached 700 something, which is very close to 800. But here we have even less than 9000, okay? We did not reach 9000. The biggest figure is 8682, okay? We are not interested in analyzing these graphs, but the point here, how to use this time plot to compare the two data. So I noticed that the two data in blue color, the cases, this is the cases of blue color, okay? If you can see, they are connected with the straight line, because this is called time plot. I told you each point will connect with a straight line. It could be also the best fit line, but here, because it's time plot, we usually connect it by straight lines, okay? Okay, so the blue one, which is cases, and the red one, which is, and the brown one, which is the death, they are very close or looks like each other with some gap or some phase difference. So here it was 0, after some time it starts 0, here it reached the peak, after few times it reached the peak, here they are almost reached the bottom. Okay, so they are very close, like they are going together. They're not 100% going together, and they cannot be 100% going together, except in very rare cases, but the normal or the general trend of them, they are the same. Okay, so what we can, if we compare the data of what, the data of cases and the data of this, we can say that the number of cases increased, the number of death cases increase, the number of cases decrease, the number of deaths decrease, and so on. So here, if we look at the pattern here, let us just read what's written here. A time plot can be used to compare 2 or more data sets. I can have 3 graphs, 4 graphs, 5 graphs, and so on. Any number of graphs, but of course we cannot have 100 or 10 or 30, because it will be invisible to us. We cannot recognize the lines from each other. Okay, so here the time plot can be used to compare 2 or more data sets covering the same period. This is one of the most important. When we present them, they should cover the same period so we can compare them. The pattern over the time for the number of flu diagnosis cases, only the cases, okay, closely resembles, very close matching or going with. Resembles means walking together or going together or approaching each other. Okay, they are closely resembles that for the number of death. Okay, so the number of cases very closely to the number of death cases, okay, of the flu, indicating that about 8% to 10% of the people diagnosed every year died shortly. So they're going together. We cannot say that 9,000 people got infected by or have or are cases of the flu, all the 9,000 died. No, the percentage between this scale and this scale is around 8%. This scale is around 8% of this one. So we can say that around 8%, and also as I explained to you earlier, that here we did not reach, we have used the scale up to 10,000, but the biggest value here is 8,000 686, and here they are very close to this one. They have reached here 738. So it could be between 8 to 10. I don't want exact figure, but I want to see the trend. It's just a comparison indicating that about 8% of the people who diagnosed every year with the flu cases, they are dying, because if the number increased, the cases will increase, but cases increase, but it's not the same figure. It is the same trend, but the percentage here 8,000 to 10,000, because both of them are almost reaching the same target here. They are not reaching, but we can assume that. Okay, so 800 as a simple way just to arrive to a conclusion, or to draw a conclusion, withdraw a conclusion from the graph. So 800 divided 10,000 equals 8%. Okay, 8%, or 0.08, which is 8%. Okay, 8 or 9 or 10%, it doesn't matter. Even within the range of 8 and 10%, it will give us an indication. Okay, indicating that about 8 to 10% of the people diagnosed that year. Okay, because all this data has been collected in one of the years, week 1 in the year, week 2, because every year has 52 weeks. So the data here collected between week 1 and week 17. So 8 to 10% of the people diagnosed that year shortly, okay, afterward the complication of flu. So they will die, or they will get the complication of flu, and they may die or pass away. Okay, I hope this one is clear.